everybody, it's Ms. Williams. This is Chapter 2, Section 1, describing the location of a distribution. So the first thing in this chapter is we're going to talk about percentiles. The p percentile of a distribution is the value with p% of the observations that are less than it. So if I was giving you this STEM plot, and I asked you to find the percentile for the student who scored a 72. So there are 25 students that took the test. The lowest grade was a 67, the highest grade was a 93. The student that scored a 72 is the second to lowest student. So there's only one student underneath him. So if I want to find the percentile for that student, I would do 1 over 25. 25 total students, I include the person who made a 72, is 0.04, or the 4th percentile. That means 4% of the students scored below him. Find the percentile of the student who scored a 93. Well, 93 is my highest grade. So there are 24 people that are underneath him. So 24 out of the 25 students who scored below a 93. So therefore, 24 divided by 25 is 96, or the 96th percentile. Percentile is always the number underneath you. Cumulative relative frequency graph. So, cumulative means it's adding it up. Relative frequency means the percent that is represented. Okay? So, this is the information about the age of presidents when they were inaugurated. So, it looks like from this table that there were 2 presidents who were between the ages of 40 and 44 when they were inaugurated. There were 7 presidents who were between the ages of 60 and 64 when they were inaugurated. Okay? So, that is the frequency. So the relative frequency is how often it happened. So I would do 2 out of the 44 presidents, which means 4.5%. Cumulative frequency, because this is my lowest group, is still a 2. Same thing. Now now we get to the second group, the 45 to 49. I had 7 presidents there. So 7 out of 44 is 15.9%. But if I'm doing a cumulative, which means I'm adding them up as I go, I would end up with 9 for this group. 9 divided by 44 gives me 20.5, which just happens to be these two, the first two relative frequencies added together. Okay? If I was going to put this on a graph, I would make age the x-axis and the cumulative relative frequency the y-axis. Okay, so here's the graph. Now from this I can answer and ask a multitude of questions. So the first question is, was Obama unusually young at the age of 47? So I would go to 47 at the age, and then I would go over till I get to the cumulative relative frequency. It looks like Obama was approximately in the 12th or 13th percentile, which means not the youngest, but definitely not the oldest. Okay, most were older than him. So I would say, yes, that's a little unusual. All right. Can you estimate and interpret the 65th percentile of the distribution? So this time I'm going to start at the 65th percentile. So I'm going to start on the left-hand side at 65. Once I get over to my graphed equation, I'm going to go down, and I'm going to see that that is approximately 57 or 58 years. That means the president that was 57 or 58 years old when they were inaugurated was older than 65% of the presidents that were inaugurated. And finally, well, not finally, we got a couple more slides, but z-score. Z-score tells us how many standard deviations away from the mean that the data point is. To find the z-score, you must know the mean and standard deviation of your distribution. So the z-score is x minus the mean over standard deviation. If the mean score of the Chapter 1 test was 81 and the standard deviation was 7, and the mean score of Chapter 2 test was an 85 with a standard deviation of 4, can you tell me if Beth received a 90 on both tests, which test did she have the better z-score? Which test did she actually score better than her peers, basically, is what I'm asking. So I'm going to find the z-score of both the first and the second test. X minus the mean over standard deviation. 90 minus 81 over 7 gives me 9 over 7, which is 1.29. The second test was 90 minus 85 over 4, 5 over 4, which is 1.25. So she pretty much is very similar. Okay, her z-score of 1 is 1.29, and her z-score of the second one was 1.25. All right. What happens if you add and subtract data to the same unit of every observation of a data set? So when you change your data set, this goes back to what I was talking about in class the other day, talking about if everybody's weight, if I took everybody's weight and found the mean of it, but then I found out my scale was 3 pounds off. Okay, so if you're adding and subtracting, you will need to change things like mean, median, quartiles, and percentiles, but you never change the shape of the distribution or the measures of spread, including range, interquartile range, and standard deviation. Okay? You can also change data by multiplying and dividing. This would be like changing inches to feet or minutes to seconds. All right? So if I'm going to change every observation in the data set, I will need to multiply or divide the value of the measures of center and location. Mean, median, quartiles does change when you multiply. The shape would not change, but the measures of spread, including range, interquartile range, and standard deviation, would change by that same unit. Okay? So standard deviation does not change when you add and subtract, but it does change when you multiply. All right. I will see you next time.